now. Can you see me? You can unmute your mic and talk.
Does you?
Good morning.
Good afternoon, sir. Good morning.
No, how are you?
Fine, sir.
Mute back your mic. So we start. Let me check if I can admit other persons in. Okay. The people I made this lecture notes for, I don't know if they are on this platform. If you are doing ND, are you on this platform? The ND2 biomedical. I don't think that they are here. But I think we should go ahead. When they finish, they can join. So what we are doing today is the Engine 221 that biomedical and P&O were unable to have time to do. These courses have been done by technology, and they have done it as an exam also in their first semester. So we are here to talk about sinusoid. Sinusoid. And by me looking at this, you will understand that this is a sinusoidal waveform. This is a This is a sinusoidal waveform. And if you are looking at it, it has its origin. Please don't mind though, there will be noise at the background because I'm not in town. So if you watch this, you will see that this wave is repeating itself, going up and down around a circle, and is complete in nature. Complete in the sense that just like a parabolic motion that originates from zero and curves down when it's descending. It has maximum points we call the E of M, and we have the peak, which most times we call the amplitude. Then it has time, it has instantaneous time, this T1. It has instantaneous voltage, this E of 1. And these instantaneous voltages are voltage at a point as the waves are going up and going down. Then it has a period. And here, we know that period is the time to complete one cycle. So as this is increasing, just like from here, it's starting from 0 to the next 0. It has completed one full circle. Then we have here peak to peak, the difference between the positive peak and the negative peak. Oh no, this thing is not moving. So this is definition of times. So this definition of term and the definition of the sinusoidal wave I've shown you. The path traced by a quantity such as the voltage in figure 1, plotted as a function of some variables that can be time, position, degree, radiant, temperature, and so on. Then instantaneous values are the magnitude of the waveform at a particular time along that the graph you are seeing at a particular instance of time. It can be voltage, instantaneous voltage, or instantaneous current. I do explain this thing to you people in class. Then the amplitude, the maximum point or the maximum value of the voltage. At this point, Once it gets to this point, it starts to descend or increase as the case may be. If you look at this point, this is the maximum point. Once it gets to this point, it's descending. And at this point here, once it gets to maximum point at the negative side, it starts increasing back. So we have the period, the time it takes to complete one full cycle, and the cycle, the number of cycles completed in 1 second. Sorry, the portion of waveform that is contained in one time, that is cycle. This from here to here. Then we have the peak value, the maximum value. This record. The maximum instantaneous value of a function, the maximum instantaneous value of this sinusoidal waveform. Who is Favor Chidima? Please hold on. We don't have lights again. I have to do everything that I can. I haven't seen that these people have started. Don't mind me, we are in Nigeria. We have to improvise. So all these things, I hope you've gone through all these things so that we meet up. We don't just waste time. We meet up because you say people are having a quiz by 7:30. Can you hear me?
Yes, sir, we can hear you.
So, and what is a sinusoidal waveform? I said sinusoidal waveform is the only alternating waveform whose shape is unaffected by the response characteristics of resistor, inductor, and capacitor elements. So, in other words, these resistor, inductor, capacitor elements, when you put them in a sinusoidal waveform like this, you still get the output this way. But in other waveforms like the periodic waveforms, if we put them, what you are going to get will be a different thing. It's either is increasing or changing or transforming the waveform. Most of you joining are from tech, and I wonder what tech is doing here. So two types of sinusoidal waveforms that we have the cosine and we have the sine wave. This is the cosine wave here, and this one is the sine wave. Sine wave always starts from here based on the Cartesian diagram we have. We have the sine from this quadrant, but cosine is always from this other quadrant or from beneath here. But all of them, when resolved, are sine wave. This thing should be changing. Okay. So this one is the mathematical equation of electrical quantities of sine waves. So this is the formula for instantaneous currents and the formula for instantaneous voltage. For instantaneous currents, the I of M, which is the I maximum, times the sine omega t, which is the sine of the angular distance. The sine of the angular distance. Omega t is the angular distance. This W is what we call the omega. I hope you are following me. This is what we call the omega, and t is the instantaneous time. This omega is the angular velocity. Angular velocity. Did I just shift this? And this is the angular distance that we are talking about. The same applies to E, where E, capital of M, is the maximum voltage, the same omega and the same distance. So this is an example of what is required. Maybe you are told to solve this. And I think I have solved this thing for those in tech, but I'll still check on it again. So, say given E, this small e, to be 5 sine alpha, which is this formula now. Determine E at alpha equals to 40 degree and alpha equals to 0.8 pi. 0.8 pi. So, and I'll say for solution, alpha is 40 degree. This alpha, which we call the angular distance. Then E is equals to 5. This 5 you are seeing is this maximum. When you see this arrangement, we are giving such a question, you know that this 5 is for the E maximum. So you just fix it and say 5 times by sine 40. This is the value for sine 40. When you multiply it with 5, you have 3.214 volts. Then for alpha equals to 0.8 pi. For alpha equals to 0.8 pi, I think I have taught you on how to do conversion from pi to degree. Tech and P and O, have I done that? You people should speak. Tech and P and O, have I taught you how to convert from radian to pi? From radian to...
No, sir.
No,
I've
sir.
not done that. Okay.
Yes, you've done so.
I will drop the formula for you on the platform once we finish this. So this is the formula. They are converting this 0.8 pi to degree now, which is 180 degree divided by pi multiplied by the radian. And the radian in this point is 0.8 pi. So when you multiply it, it becomes that this pi will cancel out, and 0.8 will multiply 180, and we have 144 degree. You now fix it back to your question, and what you have is 2.939 volts. Do you understand this one? Tech and, Biomed and P and O. Let me be moving. So, phase angle of a sinusoidal waveform. And we have that at an angle, or at a particular voltage, there is always an angle attached to it. And like we know, this is the formula for the sinusoidal instantaneous voltage. And for us to get the degree or the angle, for us to get the angle, we have to make this alpha subject of the equation, which is the angle we are actually looking for. And by so doing, we now say E maximum, we divide this instantaneous voltage, then we have it as sine alpha equals to instantaneous voltage all over maximum voltage, where alpha, which is the degree we are looking for, is equals to sine inverse of E of M. The same apply when we are discussing about the current, instantaneous current. And here it is. So determine the angle at which the magnitude of sinusoidal function V equals to 10 sine 377t. Please note that this 377t is omega. Are you hearing me? Hope you are following me. Hello? Yes, okay. So, and they said that when you apply this thing, this 377t, the value you get as instantaneous voltage is 4 volts. Is 4 volts. And then I said, again, determine the time at which the magnitude is attained. The time when this magnitude is attained. And how do you do it? First of all, you find this angle. Since they have given you the instantaneous voltage, which is 4 volts, and the maximum voltage, which is 10, the 10 is in this equation. Are you seeing my mouse? This is the 10, which is the maximum voltage. And when you do it, you have your angle to be 23.578 degrees. And they now ask you to get this omega t. So from the figure, let's check if we have the figure here. Okay, this is the figure here. When we are told to get the angle, and this is the angle, this 180 minus 23 will give us 156. They are still going to give you the same 4 volts. They will still give you the same 4 volts at their own instantaneous voltage. And when you look for the time, you are seeing the plot here. This is the 4 volts. This is the first instantaneous voltage, T1, and it goes to this point, another T2. So this point, we will check their time on this plot. So you will now convert to radian. You will now convert this 23.578 to radian, and we have 0.44 radian. And time will now be this radian, which is the angular displacement. This is the angular displacement divided by angular velocity, and we have 1.09 seconds. And the second time is 2.73 rads divided by 377 rads, and we have 7.24 meter per second. Sorry, millisecond. Any question on this particular one? Biomed and P&O, any question?
Yes, sir. The explanation is not that clear.
Okay, the explanation on this one.
Yes, sir.
Let me go back again. And this is what we are told to do. You are given this formula. The questions came in 2. You are given this formula, and we are told, 1, to find the angular distance. Are you getting me? To find the angular distance. And when you get the angular distance, you are told to find the time of this angular distance. You remember that these 4 volts will appear twice on the Cartesian diagram because it is instantaneous voltage. And this 4 volts is positive, meaning that the voltage appeared on the positive peak of, it appeared on the positive peak. Are you following me? Let me go back and show you the. So this is the positive peak. This is the positive peak, this place and this place. Assuming that 4 volts is negative, like minus 4 volts, it means that what we are going to be discussing or what we are looking for will be within this peak, within this side of the sinusoid. But because it's positive, the 4 volts will appear here and equally appear on this side. So the first time, which is T1 when it occurred, and the second time, which is T2 when it occurred, is what you are told to look for. Am I making myself clear? But before you look for it, you must understand the angle he used in appearing. And the first angle it appeared, we get it by this formula, this particular formula we have here, which is 4 volts divided by 10 volts. And you take the sine inverse of your answer, and it gives you 23.578 degree. So because what we are doing, hold on, let me still take you back. Because what we are doing, this thing from this 0 point to this point is 180 degree. And from here to here is 270, and from 270 to 360 degrees. So what we are doing is within 180 degree. So because it's within 180 degree, we will now say that the another distance, which is the alpha of 2 is 180 minus 23, and it's giving us 156.422 degree. And we will now divide because it's in there. We convert our degree to radian. This is another formula for converting degree to radian, which is pi over 180 degree times by the degree. So this degree cancels out, and we have 0.411 for 23 degree. The second one, we have 2.73 rads for 156 degree. And from our equation, we understand that angular velocity is equals to angular displacement over time. I told you that this one, omega, is the angular velocity, alpha is angular displacement, where t is the angular time. So it's just to change the equation, and we have 1.09 millisecond. And we apply this one, we have 7.24 milliseconds. Okay. And this one is the phase relationship. And we know that it's not only sine waves that are sinusoid. We still have cosine wave. But because when you resolve cosine wave, we still have sine wave, we decided to call the wave sinusoidal wave, which means a sine wave. Instead of having a cosinoid wave, we have it as a sinusoidal wave. So the relationship for the phase angle of a sine wave is A, which is the maximum point or the amplitude, sine omega t plus or minus theta. This theta represents the phase shift, the angle where a normal sinusoid should shift from what you are having. Take, for instance, this is the wave. I hope you are seeing my mouse. This is the sinusoidal wave. And this one did not start from the origin, which is 0. It cut off and start from here. So that particular angle that is cut off is this theta here. It is this theta here. It is either adding to the one that is starting from the 0 or subtracting. But on this case, we are having it as a subtract. It's removing from the one that starts from 0. But assuming it starts with 0, assuming it starts with 0, we've been doing those that started with 0, we don't need to add the phase angle. We don't need to add the phase angle. So, for positive, for angles that if the waveform passes through the horizontal axis with a positive going increasing time slope before 0, we have it as sine omega t plus theta. But if the slope, if the waveform passes through the horizontal axis with a positive going slope after the 0, we are now subtracting from this. And this becomes our answer. But because what we are doing, we still want to resolve it in the sine wave. We have to add the 90° with this, and what we are having in all this, sorry, this one is the sine part. This is the sine part for the phase shift. Okay. And this is the cosine part, sorry. I hope you are seeing the waveforms. This meeting is ending in 10 minutes. Let me check the time, please. I think I will leave out this part, which we are not going to use in the exam, and go to the part we are going to use, which is this equation, the resistors, the inductors, and the capacitor response to sine wave. And for the power line frequency and frequencies up to few hundred kilohertz, the resistors in sinusoidal waveforms does not react. It does not react. But when we start to have it at a higher frequency, like megahertz, the resistors start to have effects on the system. And from the equation that we know very well, which is I equals to V over R. I equals to V over R. We have that this V of M sine omega t, which is the instantaneous voltage representing this our V all over R. In that case, we can say that instantaneous current is still maximum current over maximum current sine omega t. Then the frequency is not affecting it. Then for inductor, when we pass this current through an inductor and we equally pass voltage, you can see the voltage, and you can see the waveform for current. Both of them are interacting. So what we are having for inductor, this is the formula for current, which is I of inductor, which is Im sine omega t plus or minus theta. Most of you joining late. And for V of L, we have what you are seeing here. This is the current starting from 0.2. Then for the voltage started like 90° before it comes here, which means the current, the voltage is leading the current. It started ahead with 90 degree. So we now have the equation for the voltage across the inductor. Then when we differentiate these currents, what we will have is omega of Im cos omega t, and that gives us an equation that is V of M sine omega t plus 90 degree, meaning that in an inductive circuit, voltage leads current by 90 degree. And this brings about what we've explained so far in the magnetism, the cause and effect. The cause and effect. And we have opposition, which is the opposition to the flow of current, is equals to cause over effect. And in this case, opposition is the resistance, which is the reactance of the inductor. And we have V of M all over current. And what we have as the opposition to the flow of current is omega L. Omega L. And this our omega is 2 pi F. Please, those of you in biomed and P&O, omega is 2 pi F. We are going to drive those ones. Those of you in ND2, I've done this thing in class for you. We've derived this formula, omega equals to 2 pi of F. Then the reactance of an inductor becomes V of M all over I of M. So the same applies to capacitor. But in this case, in capacitor, the current is leading voltage by 90 degree. And when you differentiate voltage over time, what we are going to have in a nutshell is that the current of an inductor is equals to omega C V of M. And when we do the cause and effects, what we are going to have is 1 over omega C. 1 over omega C. And we know that omega is 2 pi of F. Two pi of F. So any question? So that we meet up with the time. Any question? What is the time for you? I think we are within our time. What is the time there? That's 6:37. Any question?
No, sir, no question.
If you are in tech, you don't need to ask me question. Biomed, P&O, and ND students. E&O, are you not here?
So we are here.
Any question?
No, sir, no question.